Okay, so in this video, we're going to cover the first four problems, 3M1 through 3M4 of Chapter 3. Well, actually before that, if you are running this Colab notebook, make sure that you come up to the top, install the appropriate packages with this code here, and call up the Rethinking package. Okay. So the last two questions of the easy section had us looking at the HPDI and the PI. This is the high density posterior interval and the percentile interval. So go back to that video if you want a little bit more background on what is going to happen here. Okay, so the first two questions from the medium section are just a recapitulation of what the last video was in the easy problems, and so I'm not going to spend a lot of time on it, but it asks us to reimagine the globe tossing example, and again that's explained in previous videos, where we have 8 waters and 15 tosses, and we're going to construct a posterior distribution out of that. And the second part, or the second question, is to calculate the 90% HPDI for that. Okay, so again, if you want more on what these things mean, go back up to the video in which we cover 3E6 and 3E7. This is basically identical. Okay, but right now I'm just going to run that code. So all that I've done is I've generated samples from the posterior distribution that comes from our model of the globe tossing, which was a binomial model. Okay, and my HPDI, again, the readout on this is not great, but it goes from a P of 34 to about 73. So on this posterior distribution here, I should have put lines in here or shaded it a little bit, but it would be P values of about here all the way over to about here. Okay, and that would be my HDPI. Again, the HDPI is the interval within the posterior distribution that has the narrowest parameter footprint here and covers 90%, in this case 90%. Okay, but now onto the more interesting questions that are a little bit new. So first we'll look at 3 and then go on to 4 a little bit later, but we want to construct a posterior predictive check for this model. This means simulate the distribution of samples averaging over the posterior uncertainty and P. What is the probability of observing 8 waters and 15 tosses? So we need to go into a little bit of background to make sure that that question makes sense. So we will go into some background and then reread the question. Hopefully there's a little bit more understanding. Okay, so when we have a posterior distribution, we have a couple types of uncertainty that are in that posterior distribution, but they're not obvious. So the first type is just the uncertainty in the value of the parameter. So in this case, our parameter is P, the proportion of the globe covered in water, and we represented that here. That's our posterior distribution. And we are uncertain about the true value of P in this case, right? Because again, this is the proportion of the globe that's covered in water, and we're saying we're not really sure. We're more sure about values here than we are values here, but we don't know for sure. So that's the first type of uncertainty that we're confronted with. But the second type of uncertainty is, regardless of what the true value of P is, even if we know what that value is, when we sample, right, so the globe has an actual value for P, but when we sample from that globe, or when we create our data is finite. And so we're only going to see some limited number of samples from that parameter value. And so it's very unlikely that our data completely lines up with the actual parameter value. Okay? And so this is the second type of uncertainty that we're confronted with. Not only do we not know the actual value of the parameter, We have guesses. But when we have that, when we have a parameter value, it's going to put out data that may or may not perfectly represent the actual value of P. And so that is represented in this figure that's in the book, in figure 3.6. So here we have a posterior probability distribution, okay, which is akin to what we generated here. Okay. And any one of these values for P, I should say, whether it's 0.4 or 0.5 or 0.45 or whatever, if that was the actual value of P, for the globe in this case, when we sample from that value for P, we're not going to get all of the values lined up right at P. We're going to get a bunch of values across, right? Because our data is imperfect. Okay. So in order to capture all of that uncertainty, we would go through two steps. One is, after we generate our posterior distribution, we would sample values from it, right? We would pull one and maybe we get a 0.54 and then maybe a 0.72 and so on and so forth. And every time we sampled the P, we would simulate data as though that value for P was the correct value, okay? And so if we did that a bunch of times, so let's say I sample and I get a 0.5, and then I generate data, binomial data from that P value, I'm going to get values all around 0.5, and then I'm going to sample another value for P and simulate data. Generate another value for P, simulate more data, and when I do that a bunch of times, I get another distribution that is no longer the posterior distribution, but it's called the posterior predictive distribution. And because we went through two steps here, the two steps build into this posterior predictive distribution the uncertainty inherent in the posterior distribution, as well as the uncertainty that is generated because of the sampling, okay, the imperfect sampling that is inevitable. Now, why is this important? This is important because the model that we use to generate this posterior distribution here, that is composed of the prior and the likelihood, etc., we made that model up. Now, we used reason and educated guesses to come up with that model, but that does not mean that that model is correct. And so we want to check our model. We want to run it through tests to see, can we trust the conclusions, or to what extent should we trust these conclusions? And that is what a posterior predictive check is. And one of the ways that we can do this is we can simulate data from our posterior distribution, and if that data looks like the actual data that we observed, then we will have more confidence in the model. Or to state that differently, if the data that we actually observed is not a crazy thing to come out of our posterior distribution, if it seems like a probable thing to come out of our posterior distribution, then we can have more trust in our model. Okay, and the way that we're going to do this is exactly by following these two steps right here. Okay, so we're gonna draw values from the posterior distribution and then simulate data, put it all together, and try to see how our sample looks in comparison, or our data looks in comparison. Okay, so here is the I should well, I'll do it later. So here's the code for this. Okay, so I'm going to create a object called water 8 toss 15. So 15 tosses, we get 8 waters. Okay? And so this is going to be me simulating data. I'm going to use a binomial distribution, right? Because that is how we think that this data is distributed, binomially. Okay, so our binom creates random samples from a binomial distribution. Okay, how many samples? I'm going to generate 10,000 samples, each of them of 15 tosses of the globe. Now, what is the probability that I land on water? The prob argument here? Well, that's going to vary. It's going to vary by samples. Okay, now what is samples? Remember, samples are the values that represent the posterior distribution. These are the samples of the posterior distribution. okay? And so we're going to get samples in to the same in proportion to their prevalence in the posterior distribution. So when we're pulling samples, we're going to get more samples from, say, 0.6 than we are from 0.2. So when we draw a P of 0.6, one set of 15 is going to come from that, okay? And then the next time we draw a p-value, maybe it's 0.5, that will be the prob for that set of 15, and we do this a bunch, right? And values that are more common in the posterior distribution will be more common as the underlying probability of this binomial. So we're going to do this 10,000 times, okay? And then we are asked, what is the probability of observing 8 water and 15 tosses? Okay, and so to do that, we're going to take all of the samples, or all of they're not samples, they are simulated data. We're going to take all of the simulated data, and we're just going to count the number of times that out of 15 tosses, we get 8 waters. Okay, and then we're going to divide that by the total amount of samples that we made. Okay, 3M4 is very similar, but this time using the same posterior distribution that we found from up here. We want to now calculate the posterior predictive distribution of 6 waters and 9 tosses. Okay, 6 waters and 9 tosses. And so very similar, I've created another object here. I'm sampling from a binomial distribution, and this time I have 9 tosses according to P, proportion of water that we found in our posterior distribution, represented by the object samples. Okay. And then again, I'm just looking for the samples that meet my criteria. Okay. Well, actually, I've already ran this, but we'll run this. Okay. And for 3M3, the value that we get is about 14.75%, right? So the probability of 8 waters and 15 tosses, where we are incorporating both the posterior distribution and the sampling variance, or that's a weird thing to call it, the sampling uncertainty, is about 15%. Okay, and then 6 waters and 9 tosses, by the same logic, is just about 17%. And then here are a couple of histograms of the posterior predictive distributions for our 2 tests.